Okay, so we continue with heavy flavors at the moment at high PT, and our next speaker is Simone Marzani from Genova. So please, you have 30 minutes, and please continue.
Okay, thank you very much, and good afternoon, everyone. Yeah, so today I'll discuss some work in progress, actually, on heavy flavors at high PT. The structure of the talk is the following. In the first part, I'll try to give some introduction and motivation, and try to describe some of the difficulties that we have to face if we want to describe heavy flavors at the LHC. The bulk of the talk will be a description of a result calculation that aims to account for logarithms of the mass of the heavy quark we are considering, but also some soft logarithms that you may encounter. And then I'll finish off with some future prospects on projects that we are working on that essentially try to describe the substructure of heavy flavored jets. So introduction and motivation, heavy flavor at the LHC. So there's no need to explain the importance of studying these sorts of processes. They are very interesting from the point of view of the Higgs physics program, because we want to study the Yukawa coupling of the Higgs to the heavy fermions. As we just heard, they're also important for QCD studies because they enter PDF determination. They allow us also to study, by studying their fragmentation, we can learn something about QCD shower, and in particular, maybe, the transition to the hadronization stage. When I talk about heavy flavors, what I have in mind, really, I should have said this before, is charm and bottom. The top is too heavy, so it doesn't fragment, and we don't discuss this here, although it's fairly interesting. From an experimental viewpoint, it's possible to identify them, because essentially one can exploit the lifetime of the B or the D hadron decay, and you really see in the detector displaced vertex. Yeah, I mean, nowadays there are much more complicated machine learning techniques to do this type of tagging, but the basic idea is this one. And from the theory viewpoint, well, MB and MC are in the perturbative regime, so which means that we can do perturbative calculations for the production of these states. And indeed, there are next to linear order calculations, and they will be discussed in the following days for Z plus heavy flavor. And this is an example of now a 3-year-old paper where the Zurich group looked at Z plus B, I believe. Also, because you can keep the MBMC finite, it means that you don't, these parameter screens the collinear singularities that you'll have instead if you instead look at the fragmentation of light quarks. Now, most of the times when we think about final state, hadronic final states at the LHC, we want to talk about jets because they're easier to handle. They constitute a bridge between the theory and the experimental community. And so that's usually the language which is most common. It's not the only language, but it's the most common. However, jets with identified flavor are not that straightforward. And I'll try to summarize a little bit of this issue, although there will be a dedicated talk by Giovanni in a couple of days. So as an experimentalist, what one does usually is that the jets are defined by an experimentalist saying this way. You run a jet algorithm, which at the LHC is 99.9% of the time the anti-KT algorithm. And once you have your anti-KT jets, you run a B or a C tagger. And so first you start with anti-KT, and then you ask yourself, is there a B jet? Is there a C jet? Is there a light jet? Now, from the point of view of the theory calculation, using anti-KT is not so crucial. What you really want to do, because you're computing real and virtual, you want to sum them and find final results. And so you want to define jets using an IRC-safe flavor algorithm if you want to do flavor jet. And the problem was identified many years ago by Banfi, Salam, and Zanderighi, is the fact that if you cluster jets with anti-KT or KT, for that matter, and you define your flavor by counting the number of B and B bar, let's say, if you want to look at a B jet, this procedure is fine at leading and next to linear order, but it's not IRC safe and next to linear order. And the problem arises from configuration of this type when you can have a soft gluon which can split into a BB bar pair. That's why it's next to linear order, because you need two emission. And you see that if you recluster these Q, little q and big Q, the flavor of your jet changes. The flavor of your jet is determined by a soft emission, and this is what we say, this is the signal of ironcy and safety. Now, why do I mention this? Because in the last year, there were 4 different, this problem sort of like came into fashion again, and so there were 4 different attempts to solve this issue. Well, you may ask, but why? One thing I should have said is that, of course, being Banfi, Salamence, and Righi, not only they figure out the problem, but they also found the solution. I should have said. The issue with this solution is that the argument they devise is not anti-KT, and so it's not easy to apply it to current LHC analysis. And so try to sort of improve on this solution, which was proposed in 2006, by essentially define algorithms which are IRC safe, at least to some order, in perturbation theory, and they have exact anti-KT kinematics, or they mimic anti-KT in a good way, so that you minimize the unfolding to anti-KT jets, or they use some technique to remove sensitivity to soft physics. As I said, Giovanni will discuss this more in detail, so I'm going to just brush them. What I wanted to say is that there was a discussion recently at Les Houches this year where the 4 groups came together and tried to compare the results on the same set of data. And indeed, this is still very preliminary until Emanuele tells us that we should wrap this up. Indeed, all the 4 algorithms, they behave the same at next to next in order, or they give consistent answer. They all are safe at this order. When you start turning on the pattern shower and the organization process, they start behaving differently. And I think is a part of this, the idea of this study was to try and understand, together with the experimentalists, what is the way forward? What is the best algorithm that we should use for flavor analysis in the future? Okay, so down to the second part of my talk, which is the more, if you want, theory-driven one. This is ongoing work, close to finished, with Giovanni Ridolfi in Genova, Andrea Ghira, who's a PhD student in Genova, and Daniele, who's a master student in Genova now, is a PhD student at Buffalo. So let me take a step back. I said jets are one way of looking at heavy flavor. They're not the only way. Traditionally, especially at lab, what people would do is to identify a particular decay of a B or a D hadron, plus and measure QCD radiation. And so you measure some property of this B hadron and try to infer something about the B quark that seated. Well, either if you do this procedure, or if you go back and you do your flavor jets, you still have to face, from the point of view of calculation, similar problems. So first of all, this is a multi-scale problem. You have the hard scale of the process, the E plus E minus central mass energy at lab, or the PT of the jet at the LHC. You have the heavy flavor mass, which is typically much larger than the lambda QCD, or larger than lambda QCD, but much smaller than Q. So you have a first hierarchy. And if you were to measure, say, the PT of the B, you're done. But typically what you want to do, you want to measure some property. So some substructure or some energy fraction of the B. And so you have a third scale, which is some ratio or some fraction of the, say, the hard scale. And so you probably, depending on the region of phase space you are, you need one or even more summation to describe this process. So for this discussion, I will focus on a simpler process, so no jets, and I consider the decay of a scalar color singlet particle, a scalar in this case, but you can do the same with the Z, into a BB bar pair. And I'm going to define two dimensionless ratio, the mass of the B divided by the hard scale square, and then this X variable, which is what you usually study in fragmentation function approaches, which essentially measure the energy of the B with respect to the half of the energy of the decaying particle in the central mass frame of the decaying particle. And typically, just technical ingredient, we look at the Melling moments of the decay rate as a function of X. So in particular, we'll be interested in the region x to 1, which corresponds to the region n to infinity. Oops. Okay, so there are two conceptual ways of tackling this calculation. You can work in a scheme, which I'm going to denote as the 5-flavor scheme, but really what I mean is that the B quark is considered massless, and its mass is only retained as a regulator of the collinear singularities. If you follow this calculation scheme, that the cross-section factorizes naturally into products of a partonic coefficient function times a fragmentation function. And why this is interesting? Well, because it allows us, through Diglap evolution, to resum logs of mass of the B divided by the hard scale. Same way as it works for PDFs. What you lose is that you don't have the full kinematics of a massive B. So then what you can do is to do the calculation in a massive scheme. Of course, this is more difficult because you have more masses, you have another scale. And however, like if you go in a regime where the mass is much smaller than the hard scale, then you have large logs which are not resummed. And so ideally what you would like to do, you would like to combine these two calculations. There are a number of ways where you can do it. You can do this matching. For instance, you can do what is known as FONLL, fixed order next to leading log, where next fixed order refers to the massive calculation, and next to leading log because you resum logs of this m over pt, m over q, to next to leading log. You can do better. How does this work? Well, it's in the simplest possible way. You sum the two calculations, and you remove the double counting. What is double counting? It's the expansion of, say, the 5-flavor to some more. If you have PDFs, you have also to match the PDFs, but let's be a bit. Okay, we said then we also want to study the X spectrum. And both calculations, both massless and massive calculation, they exhibit logs which are potentially large. And these are logs in 1 minus x. So they are divergent when x goes to 1. And in Manley space, in moment space, they translate into logs of n. So they're important when n is large. And these are of soft and or collinear origin. What is the structure of the resummation of these two logs? Well, in the massless scheme, the first calculation of the first resummation of these logs was performed by Matteo Cacciari and Stefano Catani a while back, and next to leading log. Now is known actually to higher logs accuracy. The structure of the calculation is the following. You have the product of a coefficient function, Diglap evolution, and the initial condition. And because so Diglap evolution resums logs of the mass, and both the coefficient function and the initial condition are resummed in terms of logs of n. And what is the structure? C and D, they have double logs of n to every order in perturbation theory. C is not a surprise because it's computed purely massless, and so you have double logs. D, you find double logs. You have to do the calculation, but you find double logs. And Diglap evolution in MS bar only is as the cusp, as the coefficient of a single log of n to any orders in perturbation theory. Okay, you can ask yourself, what is the structure of the logs in the massive scheme? And this calculation was done by many people, in particular by Laine, Oderda, and Sterman in '98. The structure of the resummation is the following. You have the exponential of an anomalous dimension. This is sometimes called the massive soft anomalous dimension. This is now known, I think, at 2 loops, but actually we only use 1 loop, and times a coefficient function. What is the structure of this resummation? Well, here you have mass, so you only expect, and indeed you only have single logs in n to any order in perturbation theory, accompanied by a single log of the mass. The mass acts as a regulator of the collinear singularity, so you have log of the mass, log of n for every powers of LFS. You see already, what we would like to do is to, in the same way FNLR allows to match fixed order in the massive scheme to the massless calculation with the resummation of logs of the mass, we would like to do this matching also including the resummation logs of n. So that this is resummed in n, this is resummed in n and m, and you sum them together. But you see then there's a problem because the structure of the logs of n is different. Here you have double logs of n, you have single logs of n. Now it's still possible that these two guys combine so that all the double logs of n cancel. It's only an artifact of separating things. But actually it doesn't. It does in some cases, but not in general. So the difficulty in matching these two calculations is the fact that we cannot identify a double counting term. And this double counting term should be valid to all orders in perturbation theory because you try to match two resummation together. There's an additional oddity. If you take this function k, which appears in front of the resummation of the massive calculation, and you expand it at small mass, you find alpha s log square. But alpha s log square is not a log that is present in DGLAP. And we usually think that, DGLAP evolution resounds all logs of the mass, but these should be single logs. But this is a double log of the mass. So again, this is an oddity. So what is the origin of this? This has been discussed in the literature in different contexts. And I guess the problem is been discussed in different contexts that sometimes people forget, we forgot. So if you do the simplest calculation at order alpha s, and you look at the spectrum in X space, and in the massless scheme, what you will do is that you'll take your matrix element, you integrate them, and then you take the massless limit first, and then you take the x to 1 limit. And what you find is what you just said. You have a double log of x, which maps in double logs of n, and a single log times the log of the mass. If you do the limits in the reverse order, which is what you would do in the massive scheme, then you only have a single log of x, 1 over 1 minus x times the log of the mass. So it's clear that the two limits do not commute. For instance, if you try to do the same for Drell-Yang kinematics, so BB bar into X, the two limits do commute. And you can match the two calculations without a problem. I should say, Corcella and Mitov pointed this out in the context of deep inelastic scattering. Aglietti, Ferreira, and collaborators in the context of B2S gamma decays. So what is the origin of this mismatch? If you go back and you take the Rissan formula in the massless case, at least an X-leading log, you can write it in this form. So there's some prefactor, which are not so crucial for us. This essentially is the evolution part of DGLAP that doesn't contain logs of n, so we're going to factor it out. The important thing is you can write it essentially as the product of two jet functions. And if you take the jet function, which refers to the B quark, which is the one you're measuring, then essentially contains a contribution from the coefficient function, from DGLAP evolution, and from the initial condition. And you see that these two contributions exactly cancel, and you get back only single logs. So the measured jet function is not a problem. So this is another way of saying that the two limits commute for this guy. However, the unmeasured recoil jet function, it's computed in the massless limit, and it has a double log, and that double log doesn't cancel against anything. So double logs of n purely stems from the recoil jet function. So how do you go about this? Well, you can notice that the two jet functions are computed in different limits. The measured jet function, because you want to keep information about the mass, is computed in what is known as the quasi-collinear limit. So the limit where kt goes to 0, m goes to 0, but the ratio is constant. On the other hand, the recoil jet function is unmeasured, and so it's computed in the massless limit. And because it's computed in the massless limit, it has double logs. And so the solution that we arrived at, which was actually the same found by Aglietti and collaborators, is to compute the recoil jet function also in the quasi-collinear limit. Another issue that we found was not very discussed in the literature was that because you're dealing with, you're treating sometimes the B quark as massless or massive, typically when you do resummation, you integrate over the running coupling, and so you cross thresholds, and so you change the number of active flavors. Okay, so resummation usually is done in Mellin space, but when you start crossing thresholds, at least for us, it was difficult to understand how to properly describe this into Mellin space. So we decided to do the calculation in physical space. And I don't want to describe the calculation details, so I'm going to draw some pictures. And the picture that I'm going to draw are these Lund plane. Lund plane are a way of describing the emission of soft collinear gluons, and in terms of two kinematic variables. On the vertical axis, the logarithm of kt divided by the Hart scale. And on the horizontal axis, either the rapidity with respect to in this case, the B bar, this is the B bar direction, or the angle, emission angle with respect to this direction. So B bar is going this way, B is going this way. And lines, these two lines define the kinematic limit, the Z to 1. Whenever you have a bar, it's because I'm measuring something with respect to the B bar, but there's no bar with respect to the B. And these lines define the observable I want to measure. And if you, essentially the interesting, well, the handy way of this diagram is that by just drawing lines and coloring areas, you work out, you have an idea what the next leading log resummation is going to be. So the pseudo-comfort factor associated with the resummation is this green area. So what happens if you add masses? So this is all massless. Well, you have to take into account the fact, that collinear emissions are suppressed. This is the dead cone effect. So collinear emissions means emissions which happen at angles which are larger than some angle psi are suppressed, which means they don't exist anymore. And that's why this area is not colored anymore. And same when you have emission collinear to the B. And there is also a new horizontal scale that appears, which is the scale where the transfer momentum of the emission equals the mass of the quark. What is important, because alpha S is evaluated the transfer momentum of the emission, and so when you cross this value, you go from, say, 4 flavor to 5 flavor, 4 flavor to 5 flavor. Okay, so now what we have to do is essentially to draw pictures which refer, this is for a generic observable V. Now we have to look at the observable that we want, which is 1 minus X. I choose 1 minus X because I'm interested in X goes to 1, and I like observable that go to 0 in the soft limit. I need the parameterization of the observables in the region collinear to the B and collinear to the B bar. And you do some simple kinematics, and you find that this is the energy fraction of the gluon. This is expected. And instead, if you are collinear to the B bar, 1 minus X essentially corresponds to the invariant mass of the recoiling jets. Again, simple kinematics. Once you establish this, then you turn the crank and compute the areas that correspond to pseudo-comfort factor. And these calculations, at least for me, are quite natural because they're the same calculation that you do when you do just substructure. Okay, if you want to reach next to linear log resummation, I mean, this picture needs to be a little bit modified. You need the full splitting function, you need alpha S at 2 loops, you need the 2-loop Caspar anomalous dimension. These are all technical ingredients that you need to put in. So what you find is that there are actually different regions. And the different regions depend on the relative size of the observable, 1 minus X, and square root of psi, so M over Q. So if you are in a region where 1 minus X is bigger than square root of psi, you're here. So this is the jet function, in red, the jet function of the B, and in blue, the jet function of the B bar. In this region, you see you are, essentially you reproduce the calculation by Cacciari and Catani because you are far away from any threshold. So the calculation leaves, apart from the initial condition, all the calculation leaves in the 5 flavor region, and it's essentially a massless calculation. And in particular, if you look at this blue triangle, this blue triangle is far away from anything that has to do with the masses, this line and this line, and so in particular, it's a massless calculation, so it has double logs, as we found at the beginning. Now you lower your observable, and you enter this intermediate region. 1 minus X is between square root of psi and psi. Now again, this blue triangle is again massless, but you start gaining sensitivity because it dips into the 4 flavor region. And so the calculation by Cacciari-Catani is corrected by some contribution that also know about 4 flavor. And if you go down again, then you really feel the dead cone here, because you see that now I cannot color up until the kinematic limit. So the dead cone, which is this vertical line, permits me to go into this region here. And what this does, it cuts off the double logs. So you only have a single log of soft origin times the log of the mass. And so in this region, you only have single logs. So this picture allows you to understand that there is no contradiction. The two limits don't commute, but the two limits live in different regions of phase space. So if you are in the massless case, then you have double logs of n, or double logs of 1 minus x. If you are in the massive, which is this one, then you only have single logs. But if you want these double logs of n, they don't live here. Actually, what they do is they turn themselves into logs of the mass. So the double log of n becomes a double log of the mass, which is precisely what we found by expanding the resummation of the formula by Sturm. So this calculation is done in X space. How you do go back to Mellin space, because at the end we want to match to the usual calculation. You can notice that a next leading order, pardon, a next leading log, you can simply identify 1 minus x with 1 over n bar, with n bar being n times e to the Euler gamma. And this is enough to capture the this logarithmic accuracy. Now, beyond this, it's more complicated. Okay. So we have some first results in n space. On these plots, these are for 2 different values of the hard scale. This is square root of q squared 25 GV, and this is instead an on-shell Higgs. Now here, this is an n space, and I put vertical lines where essentially the transition points in X space are mapped to. And the idea is that when you see something in full color is where the curve belongs. So for instance, if you take this gamma 1, it belongs in this region, and then here is shaded because it doesn't belong here anymore. And same if you take gamma 3, it belongs here, and in this whole region is shaded because it's the wrong region for this one. So the first thing you notice is that this effect, gamma 3, so this is the massive region, is important only if you have a hard scale which is not so hard. If you look at the instead Higgs decay is not important. Actually, you reach the Landau pole before reaching this transition point. The other thing you discover is that here you see essentially only here there are 2 lines which are superimposed, and essentially it turns out that this intermediate region, from a numerical point of view, for this process is completely identical to the first region, just drawn also in here. So if you want all this, the gymnastic of this region from a numerical point of view is tiny. Okay. So in the last 3 minutes, some outlook. So what are the prospects for heavy flavor jet substructure? So in order to achieve this consistent resummation of mass and soft logarithms, we actually had to understand jet functions in the quasi-collinear limit. Now, we know we can now take this type of calculation and apply them to a wide class of jet observable. And this would allow us, we only started to sort of like open a different, looking at, say, heavy flavor process with a different eye. So essentially try to build up a new jet substructure process at the LHC for heavy flavor. And so, for instance, one powerful variable that one usually studies in the context of jet physics are these jet angularities. So these essentially measure these are sums for over all the particles in the jet of the PT of the particle divided by PT of the jet, weighted by the angle, the opening angle in eta phi of each particle with respect to the jet axis to some power. So alpha equals 2 is usually called jet thrust, alpha equals 1 jet width, and alpha equals half is the resolution angularity. So these have been studied, computed, and measured at the LHC for light jets, and now we are in position to start drawing Lund diagrams, and so start doing calculations for these observables with massive quarks. So you see that the feature being these vertical lines which denote the dead cone for each of these variables. This is ongoing work in collaboration with Prasanna Dani, who's in the audience, Oleg Fekevich, Andrea Gira, and Gregory Sway. You can also try and design new way to expose the dead cone. Dead cone is a QCD effect, which has been actually first measured at the LHC only last year by the ALICE collaboration with a very beautiful measurement looking at C of D meson, so C quarks. So jet grooming is a technique that allows us to remove soft radiation, and since the dead cone is a collinear effect, if you look at the Groom jet, when you only have collinear dynamics, then this should expose the dead cone in a more pronounced way. There was a recent paper trying to design some jet grooming irony precisely for this reason. And what we start doing is to instead we took a very well-known grooming algorithm, which is soft drop, and try and understand how the presence of soft drop, what is the interplay of grooming and having a dead cone effect, and try to start studying properties of groom jets measured on jets which have this additional scale in the game. No results here because this is something just started. Okay, so this brings me to my conclusion. So IPT processes would identify flavor, being the flavor jets, or identify hadron on decays, offer a complementary handle to study flavor physics at the LHC, complementary to what is done by the LHCb collaboration, let's say. The presence of multiple scales requires usually one resummation, and these two resummation, combining these two resummation is not always straightforward. But I think now, we understand the basics of it, at least an extra linear log. And so we actually are in a position to take what we learn from just the structure studies of the past 10 years, what is known about flavor physics, and try to merge them together to study heavy quarks from a different perspective. And if you're interested, just an advertisement, we are organizing a small workshops in Edinburgh at the end of November, beautiful weather, discussing these topics. Thank you very much.
Okay, so thank you for this nice talk and for keeping the time. Perfect. So, questions, comments, remarks? Oh, yes.
Thank you. So I have a possibly technical question for you, Simone. As you said...
You said technically, not 10, right?
Technical.
Okay.
As you said, I mean, you set up everything with your Lund, and then you start doing your calculation, which are typically things that you've done hundreds of times now, so everything goes in a straight line and you know what to do, right? But there was a thing when we were doing the paper you mentioned with Alba and Letizia that sort of posed the issues. And these are related, I think, to the other effect that you see, that is the double limited do not commute. And that is, how do you actually treat your splitting function? Because as you know, what is typically done in sort of the just substructure calculation, you take your full splitting function and then you expand in x, right? And you just keep the 1 over x term, and then you add the BQ term or BG term, depending on which splitting you have. But then the thing is, as you correctly said, the x expansion and the m over q expansion, they're two different expansions. Then with the parameters, when they're similar, you cannot do that anymore, because the massive term in the splitting function scales exactly like x. So you cannot drop it. If you keep the other, you cannot drop the massive term, and if you keep the mass term, you cannot drop the other. This is what we saw, at least.
So, yes. So I think, okay, it's a bit technical. So I think you're right. So you have to keep this the m over x term in the splitting function, and what we seem to see, but the paper is not published, so we might be wrong, is that what you have is if you are in the massless regime, you have this B coefficient, BQ and BG, and I would say quite smoothly they turn in what in the literature are called the H coefficient, which are what you get from the massive soft anomalous dimension.
Okay, but when you do these things, you keep the full splitting function, then you expand afterwards, yes, after the integrals. Okay.
Okay, so further questions, comments? Oh, yes, Sven?
You see any relation how to formulate this in theories like soft collinear effective theory?
Okay, I'm starting. So I gave a similar talk by the Blackboard in Vienna, and I was asked the same thing, to which I replied, you should tell me, I don't know. So I think in ICT, so in effective field theory, you definitely have different effective field theories for the different regions. What is not clear in my mind is whether they in some of this paper, they also consider the fact that they don't necessarily match So the fact that the limits don't commute, they don't necessarily match. So for instance, Martin Benecke gave a talk, seemingly a completely different topic, which was he was looking at electroweak resummation and for the endpoint of the photon spectrum. And actually it's the very same issue, because you have it's an endpoint, so you have logs of this resolution parameter, which is the same as 1 man of x. And he was showing that it did different effective field theory, depending on the relation between this resolution parameter and W, let's say. And he did comment that analytically they don't agree, but numerically they overlap quite nicely. So I don't know if there is a mechanism to make the whole thing smooth in SCT. Maybe there is.
Okay, further questions? Comments? So, do we have some time? Yeah, okay, so one more very quick question. So in the beginning you mentioned these heavy quark taggings, right? And the possibility that the flavor of the jet is coming from some soft heavy quark, right? So if you have a heavy quark which is soft, so to speak, the left frame is very close to the rest frame. So if the tagging is using some secondary vertex displacement, in that case, how big this displacement can be? So is it possible to really resolve this with the vertex detector? Right, so maybe this is trivial and we have to sit down and work out the numbers, but...
okay, these are, I'm not...
But
so
this is a very technical thing, right? It's just maybe some food for thought.
Okay, no.
I'm just a simple comment, right? Because if you have some massive object, if it's soft, it cannot really move too much.
So the question is more from the displaced vertex from the...
Exactly. But if the tagging is using a different
So no, but this jet tagging, okay, it depends which side of... So the experimenters will run something which essentially exploits this impact parameter, so low. In reality, they have, at least Atlas has a very complicated multivariate technique to determine whether this is a B or not. Now, what I was referring is, what happens, so and once you have that, they essentially count. So do you have a displaced vertex which is a B? Yes. Close to the jet axis? Yes. B jet. Now, this counting for anti-KT jets is not IRC safe, and this is the thing that I mentioned briefly. Now, how efficient is the experimental B tagging? This I'm not sure.
Yeah, that's a different question, yes. Okay. Maybe some further comments? If there is no further comment, thank the speaker again.
Before going to the coffee break,